So there are several applications. Some of them we will mention. The first is the power of matrices. So if you want to get the power, not just 2 or 3, maybe 1000 power and so on. So if you multiply 1000 times that given matrix A, certainly it will be a time consuming task. So the idea is that if you can diagonalize that first, so that means if our matrix is diagonalizable, meaning that there is a matrix P, so that P inverse AP is D, that is the diagonalizability. So if we can diagonalize that matrix A, then it is easy to get the power. Why? Because A is nothing but PD P inverse. Out of this relation, A is nothing but PD P inverse. Just try to get what is A square. So A square will be simply PD P inverse multiplied by again PD P inverse. So PD P inverse multiplied by PD P inverse, and then P inverse P, that is the identity matrix. So what you get at the end, it is P D square P inverse. And the basic idea, basic principle behind this, why it can be used for getting the power of matrices, as you can see in the A square itself. So A square is nothing but P D square P inverse. So this D square is very easy to compute. Yeah, you get the idea. If you have a diagonal matrix,
Yes, sir.
what is it? Is square? The square of the diagonal entries.
Yes.
Right?
Yes, yes, sir.
Yeah, so that is the beauty. So if you have lambda 1, lambda 2, lambda 3, the diagonal matrix, if you square it, you will simply get lambda 1 square, lambda 2 square, lambda 3 square, and so on. The rest, everything will be 0. So with this, if you just compute A3 or you compute A4, in fact, or whatever, if you compute AN, the idea is that AN is nothing but P D power N and P inverse. Yeah, P D power N, P inverse. So you need to just get the power of that diagonal matrix, nothing else. You have A power N is equal to P D power N and P inverse. So you will get this power of D. So D power N. That's all. So when we are talking about, the large power, see, in case of you have A2 or A3, you can directly multiply. Naturally, why you will compute P and P inverse, because that is also time consuming. But when we are talking about A power 1000 or something, then you need to do a lot of, multiplications here. You need to do a lot of multiplications when you have A power 1000. But if you get just your P and P inverse, then this multiplication, that means D power this 1000 is nothing. That's just the power of the entries in the diagonal of this matrix D. And then this is, I mean, as you can realize, this is much more simpler than getting the power of A. So here just an example to show. I mean, this is not the best example probably to consider here, because A power 5 is still okay. You can, compute this 4 times multiplications, etc. But if you have very large power, then it is a good idea to go ahead with this approach. So anyway, just to demonstrate, so you have eigenvalues here -1 and 2. Matrix can be diagonalized naturally because you have distinct eigenvalues. And once you compute the eigenvectors, you will see it's a 2, -1, and 4 and 1. So if you take this P 2, -1, 4, 1 as the column elements, then P inverse you can compute, and A power 5 will be P D power 5 P inverse. And when you just put it there, your P and your P inverse, and then D power 5 is simply -1 power 5 and 2 power 5, because the D, that your diagonal entries will be the eigenvalues -1 and 2. This is your D diagonal element of this D are -1 and 2. So you have -1 power 5 and you have 2 power 5. And then you multiply this. So you have only 2 multiplication with this, and then finally one more. So only 2 times you are going to multiply it, and you will get the answer. As 21, 44, 5.5, and 10, which you could have, of course, got by multiplying that A 5 times. Well, So I hope this is clear, right?
Yes, sir.
Okay, very nice. So the another example, which is of course more important and very much applicable, that is the solution of system of linear equations. So you are already familiar with system, maybe not the system of linear equations, but at least that differential equations you are familiar with. So I think in this first part we taught you differential equations, but we could not go up to the system part, if I remember correctly. So, but we can solve that system of linear equation, and one reason is that actually those system of linear equations fit very well once you have the idea of these diagonalization, because there also we solve by doing the same thing what I will be showing here, but not naming them as eigenvalues, eigenvectors, and that matrix P. So we do some kind of indirectly the same thing, which is not so nice. So here it is really well fitted that how to solve a system of linear equations once you have the idea of diagonalizability. So consider this system of linear equations. So how many students have joined now? Let me just see. Okay, 126. All are not joining. Yeah, so you should all attend the lectures. I don't think it's really they are not worth. So I think it's you will get some better ideas. So consider the system of linear equations. X dot means you have the vector here of derivatives. So if your variables are x1 and x2, so here you have dx1 over dt, then you have here dx2 over dt, and then the right hand side you have basically you have the system. So anyway, first let me write down without this matrix and all. So we have two equations, for example, we can have 3, 4 or whatever. So dx over dt, we have, let's say, 2x1 plus 3x2. We have another equation dx2 over dt where you have 5 times x1 plus x2 and so on, right? We have a system of linear equations. System means you have more than one equations, so more than one dependent variable and one independent variable, because we are talking about ODEs, ordinary differential equation. Whenever you have only one variable, they are called ordinary differential equations. When you have more than one variable, these equations are called partial differential equations. So we are talking about the ordinary differential equations now. So we have two dependent variable x1 and x2, and their relation with the derivatives are given here in the first equation, here in the second equation. And our aim is to solve this to find the solution of this system. They are coupled, right? So the x1 equation has this x2 and x2 equation has x1. So they are coupled. You cannot solve just one equation independently and then solve the second one independently and then get your x1 and x2. That is not possible. Yeah. So there should be some ways to really solve this. And in practice, you have a large system. I mean, not just 2 by 2. So we can write down this system as in the vector matrix form. So here the vector will have these derivative terms dxt, dx2, dt terms, and the right hand side you have 2, 3, and 5 and 1, and then you have again here x1, x2, right? So we have written in this form. So this is what we are calling x dot t, and here we are calling a, and here we are calling this xt. Is that clear? The representation here.
Yes, sir.
Okay, good. So we have this system of linear equations written in this format. X dot is equal to ax. This is eventually what I have explained here, nothing else. Just the way of representing. Good. So we assume that A is diagonalizable, and that we have to assume. Otherwise, I mean, that's the application of the diagonalizability. If it is not diagonalizable, then at least this approach, what we are explaining, will not help. Then there are other ways, little more complicated, which can be used for solving such systems. So when this is diagonalizable, we can have this D is equal to P inverse AP, and or A is equal to PD P inverse. And then we have this x dot is equal to a is PDP inverse, and you have xt there. So this a is replaced here by this PD P inverse. Well, so we have the P inverse xt, P inverse xt is equal to d P inverse x, d P inverse x. And this again we can write down as, because see, the P is something constant. Yeah, these are the coefficients are constant. There is nothing of T. Sorry, there is nothing like T there. So they are just constant. So we can have like P inverse xt and then the prime. So the derivative of everything, because that constant has nothing to do. You can always bring them to the front. Then the right hand side we have d P inverse xt. I hope this is clear. Yeah, so we started with our system of linear equations, then multiplied both the side by P inverse, and this is the result. And we have clubbed this P inverse xt prime and is equal to d P inverse xt. Well, so this P inverse xt is a new variable you can set here. So P inverse, because this is a matrix, P inverse and xt is a vector, and the multiplication will be again a vector. So this yt is a vector. So this yt, here we have yt and this is the prime, and then you have d, and then here you have also yt. So what is our system now? Our system has reduced to this notation now, that y prime is equal to d yt. What is the benefit now here? Can someone tell me? We have this system. By this some manipulation, we got another one. Y prime is equal to dy.
Sir, all the equations became independent of each other.
Yes,
And this is
exactly.
not
Because
different.
here the d is sitting, absolutely correct. So if d is sitting here, so you just take a close look at what are these equations now. We have the first equation like d1 dt is equal to, because here the diagonal entries will be there. Yeah. So second we have dy2 over dt. So let me just write down in matrix form. Then you have some d, whatever you 1, 3, 2, 5. I don't know what it will be coming. Oh, not this one. Sorry, it's a diagonal. Right? So the D is something like 1, 5. And then you have here again y1, y2, right? So what is this first equation? Your first equation is dy1 over dt is equal to just y1. The second equation is dy2 over dt is equal to just 5 times y2. So we have two equations and they are decoupled. They are not coupled. They are uh, non-coupled equation. The first one is dy1 over dt is equal to y1. You know how to solve that. This is not a system anymore. The second equation in y2. So you have dy2 over dt is equal to 5y2. This is not a system. So now we started with a system and we got two decoupled equations which can be solved independently. Yes. So this is the idea of the diagonalizability. The application of this diagonalizability. And once you have y, because out of this you will get this y vector, right? You will get y vector. But we know that relation from here, that xt is nothing but it is pyt. So xt is nothing but pyt. So at the end we will just multiply by that matrix p, and you will get this xt. So this is fine, yeah, acceptable. So you have xt is equal to p y t. Clear?
Yes, sir.
That okay? Fine. So you have, I have already explained you. So you have here the diagonal matrix, and then these equations are decoupled now. And finally, your solution for each of them, you know, right? The solution, you know, y prime, yi prime is equal to lambda yi. You know the solution of this. What is the solution? Yi is ci e power lambda it. This is the solution of this simple equation. And so you have solved for y1, y2, y3, and so on. Or for all, you have the solution there. So ci's are some arbitrary constant. And then at the end, your y xt will be just pyt. So what is your solution in terms of xt? You have x1, x2, x3, x1, xt, xn is equal to. Just remember your P, that model matrix has the entries, the first column, the first eigenvector, right? The V2, the second eigenvector, and so on. You have those n eigenvectors. and then we are multiplying by y. So y1, y2, y3, yn. Correct? So this matrix vector multiplication I have written in this form, that this column multiplied by y1. So y1 is nothing but c1 e power lambda 1, and then this vector. The second vector y2. So this is the vector y2 and c2 e power lambda 2t, and so on. Then you have cn, and then you have the last vector here yn, and then you have e power lambda nt. Correct? So is that clear? That how we got this equation, that c1, this is a vector here v1, the eigenvector actually, and e power lambda 1t, c2 the second eigenvector e power lambda 2t, cn this. So this is the solution now you have for x1, x2, x3, xn.
So here
So
lambda 1 and lambda 2 up to lambda n are eigen values in the eigenvalues.
Yeah, these are the eigenvalues, right? Lambda 1, lambda 2, lambda n will be the eigenvalues because they are the diagonal entries, and those diagonal entries are the eigenvalues, nothing else. So directly the solution you can write down. If you have the eigenvalues, eigenvectors, you compute the eigenvalues, eigenvectors. So constant, eigenvector, and e power lambda, the corresponding eigenvalue, right? C2 eigenvector e power lambda t, and so on. You can write down directly the answer. What you need? You need eigenvalues. You need eigenvalues. You need eigenvectors. That's all. For a given system, you compute eigenvalues, eigenvectors, and then you are writing actually the solution directly. Fine?
Hello, sir.
Yes.
Sir, the eigenvector is corresponding to that eigenvalue.
Yes. Yeah, that will be automatically there because in your P, the first V1 will be corresponding to, in D, it will be lambda 1 there. The first column
Okay, sir.
here will be corresponding to that lambda 1. So this lambda 1
Yes, sir.
corresponds to this vector, lambda 2 corresponds to this vector, and so on.
Excuse
Any
me,
other
sir.
question? Yeah.
Sir, but even if the A is non-diagonalizable, still you will get eigenvalues and eigenvectors. Then how we can say answer is correct or wrong?
No. Because this is, see, we got with some process, right? It is not something that we have just written this randomly. We got through a process. So it will not work if you have a matrix which is diagonalizable and then you will write e power. See, there will be repeated eigenvalues, true?
Yes, sir.
So if
It's
you have
not
lambda
diagonalizable.
and lambda, so you will get e power lambda. Correct?
Sir, but if it is non-diagonalizable, then we will get same at least two same eigenvectors, no, in that case. So
Yeah,
then
that's what I'm saying you, that your V1 and your V2 will be the same. Let's say if lambda 1 and lambda 2 are same and corresponding to that, you got only one eigenvector. Then it is not diagonalizable. So suppose
yes,
in an example, you have lambda 1 equal to lambda 2 and corresponding to these two, you got only one eigenvector. Correct?
yes,
This is
sir.
the situation that matrix will not be diagonalizable.
Yes,
True?
sir. Yes, sir.
So this writing this does not make sense now because you have e power lambda t, and these vectors are same. So you are getting just one constant. You are getting just one constant there. So you are not getting even n arbitrary constants. Whereas the system says you will get n arbitrary constant if your system has n equations. So that is not the solution. What I am trying to say, if your matrix is not diagonalizable, you cannot write this.
Yes, sir. Yes, sir.
Right? Okay, so if there are no questions, then we do one example just to complete this. So we have a system of linear equations dx1 dt is equal to 3x1 2x2 and dx2 dt is 7x1 and minus 2x2, right? And if we rewrite that system of differential equations in matrix notation, then we are getting x1 x2 prime, and then we have here 3 2 and 7 minus 2 x1 x2. Fine. This is what this system is written as. Okay, so we have this matrix A, and you know what to be done now. So for this matrix, we need to get the eigenvalues, and eigenvalues for this matrix, once you compute, will be -4 and 5. These are the eigenvalues. Eigenvectors will be 2 minus 7. I am just skipping that part. You have to practice yourself. So corresponding to -4, you are getting this eigenvector. Corresponding to 5, you are getting one eigenvector. And then your solution, I am writing just the solution because theory we have already discussed. That will be C1, the first eigenvector here, let's say 2 minus 7, and e power -4t, correct? C2, the second eigenvector, and e power 5t. So you got the solution. Your x1 is like 2c1 e power -4t plus c2 e power 5t. Your solution x2 is c1 and minus 7 times c1 e power -4t, and then you have c2 e power 5t. Correct? We have the solution. So this eigenvalues, eigenvectors plays very important role for finding out the solution of such systems. Good. So I don't think there are any questions, or there are. Okay. So the conclusion is that we have gone through this very interesting chapter on diagonalization of a matrix. So where we have seen that how to get the power of the matrix, and in particular in the second case we have seen that how to find the solution of system of linear equations when that matrix is given, matrix is diagonalizable. Correct? So this was on